Let's talk about springs. People love springs. They love drinking fresh spring water. They will travel thousands of miles for the opportunity to bathe in hot springs. They will trek for an hour or two down an otherwise very boring trail just to see the springs at the end of that trail. But what are springs and how do they form? In fact, how does water move underground at all in the first place? And how does that impact every single river, lake, spring, well on our planet? I'm Craig the geologist. Come find out with me. It rains. Water falls from the sky and hits the land. That water soaks into the soil. A very small amount of it is retained by the soil, and the rest of it filters through the unsaturated soil down to the water table. What's the water table? Water table is very simply the level that the groundwater is at. If we have our ground surface here, we'll make it a grassy one. That's grass on our ground surface. The water table is simply the top of the saturated zone. So down here, if you dig a well, it's going to be filling with water. Up here, it might be damp. Water might be filtering down, but it's not fully saturated. Down here, fully saturated. Once reaching the water table, that water will flow very slowly in the direction of groundwater movement. And yes, groundwater does flow. In fact, if it didn't flow, the entire planet would be a wetland, basically. Rain would continue to fall and the water table would just rise up until it reaches the surface. So obviously, groundwater must move, or else we'd all be ankle deep in water right now. The way that water is stored or flows underground depends on the characteristics of the ground, rock, or unconsolidated sediments that it's flowing through. And so I'm going to throw a couple of terms at you. The most important of which are porosity and permeability. Porosity is a measure of just how porous a rock, or we'll call it a medium, any kind of material, whether it's consolidated or unconsolidated. It's a measure of how porous it is. How much pore space is it? And it's a very simple thing. It's a ratio of the volume of solid materials to the volume of empty space that is in with that material. And that's largely determined by the grain size of the material. Let's do a little thought experiment here. You're at a jumble of giant house-sized boulders. As they're all leaning against each other, they're not packed in very tightly. You can walk between them pretty easily. You can have waterfalls cascading through the center of them. There's lots of empty space in between. Now, if you take fist-sized cobbles and put it together, you're going to have much smaller pore spaces in between. And if you take sand, I've got a little glass of sand here, the pore spaces will be even smaller because those grains can pack together. So it's not just a matter of the pore spaces being smaller, but there tends to be less of them also. And once you get down to a consolidated sandstone, well, now you've got very little pore space. And if you get to like a granite or a chert, there's virtually no pore space whatsoever. So materials with a high porosity, things like sand and gravel, things with a low porosity like limestone, chert, or granite. And then you've got permeability. Permeability is a measure of how connected those pore spaces are. Just because you have a lot of pore space doesn't mean that material from one pore can flow into the other if they're all separated. For example, if we have pores that kind of overlap, well, the water is going to be able to move pretty easily through there. It's going to be very permeable. However, if we have a rock where the pore spaces are very spread out and not connected with each other, it's very hard for the water or any other liquid to move through that rock to get to the other pore spaces. So this is a rock with a lot of permeability. This is a rock with very little permeability. Let's look at a few examples of that. We have, well, let's begin with the sand here. Sand has a lot of pore space in it. I mean, you can see this thing's just wiggling around here, so it can bounce around pretty easily. It becomes a little bit like a fluid when you wiggle it, and that's because of all the pore space that's in there. And it's also very permeable. Those pore spaces are connected very easily, very loosely, and water can flow between them pretty easily. This is a piece of pumice. This is incredibly light. It has a lot of pore space, but those pores tend to be all separated by very impermeable layers. Here's a piece of scoria on the other hand, and scoria tends to have a lot of pore space. This is a similar density, a little bit more dense, but not much more dense than the pumice. But those pore spaces are much better connected, and so it's a much more permeable rock. Sandstone tends to have higher permeability and porosity than most rocks, but it has a lot less than the unconsolidated sand because those sand grains have all been mineralized together now. And once you start getting to more dense rocks like limestone and chert and your granite, you're going to have very low porosity and very low permeability unless there are a lot of fractures in the rock. Now, of course, if the rock is very highly fractured, then that creates space in there that increases the permeability a little bit, or increases the porosity a little bit rather, but significantly increases the permeability because now liquids can flow through it very easily. And the measure of how well a liquid can flow through a rock is called hydraulic conductivity. Now, we're not taking a very deep dive into this, so you can consider hydraulic conductivity and permeability to be roughly the same thing. They aren't the same thing, but we can treat them for our purposes today as if they're the same thing. Let's have a look at a couple of different types of rocks in terms of porosity, permeability, and hydraulic conductivity. And let's begin with the pumice. Now, pumice has a very high porosity. In fact, it is up to 90% empty space inside. Now, that's a maximum value. Pieces like this are more typically 60 to 70% pore space, but that's still a lot of empty space in your rock. However, it has very low permeability. All of those tiny microscopic air pockets and the larger ones you see tend to be isolated from one another. And that results in it having very poor permeability, very poor hydraulic conductivity. Now this is scoria. Scoria is actually a very similar rock to pumice. It is erupted similarly from volcanoes. It is a lot of pore space. It tends to have a typical porosity of between 40 and 60%. So a little bit less than pumice, but not massively less. But unlike pumice, the holes are well connected. It has a very high permeability and an incredibly high hydraulic conductivity. Now that difference is probably best illustrated with a float test, which I'm going to mime for you here. We start with the pumice. It has a lot of empty pore space, but those pores aren't connected. They're all sealed off, and it floats as if it were styrofoam. Scoria, on the other hand, similar density, similar amount of pore space, but it sinks like a rock because those pores are well connected and the water flows right through it. It doesn't trap air inside, allowing it to float the same way pumice does. Pumice, high porosity, terrible permeability. Scoria, high porosity, high permeability. Now, returning to our other rocks, and these are a bit more common than scoria and pumice, sandstone is probably the most porous and permeable of the common rock types on Earth. Here's limestone. This is a very common rock type as well. This tends to not have very high permeability and porosity, unless of course it's been worked on by acid and created a massive cave network, in which case you have the opposite situation. Here's chert, another pretty common rock type, and guess just how much empty pore space and permeability there is in this rock. It's basically like porcelain. And then we've got granite. Now, granite tends to have almost no empty pore space, and it has very low permeability because there's nothing to connect in terms of pore spaces. It was a magma that crystallized underground. There weren't air pockets to be formed in there. Now, for a piece of granite that doesn't have any fractures in it, the hydraulic conductivity is incredibly low. If we place a droplet of water on there and we assume there's no evaporation, it would take about 275 years for that water to penetrate 1 centimeter down into the granite. It is not hydraulically conductive. Of course, if there are cracks in there, then that water is going to flow through pretty quickly and easily. You have a different situation entirely in that case. With chert, if it's unfractured, you've got a similar situation, similar hydraulic conductivity. If there was no such thing as evaporation, you could spend your entire life waiting to watch this water soak into the rock. It would eventually, but it would probably take longer than your lifetime. Limestone has a much higher hydraulic conductivity, but still relatively low. For this droplet to penetrate 1 centimeter in the rock will take about a full day. Now that's different if there were cracks in the rock, and if there's a cave network, it would flow through instantly. Sandstone tends to be highly variable depending on the grain size and the degree of cementation. That's the amount of mineral filling in those pore spaces. But a typical range of hydraulic conductivities for these rocks would mean that it would take between an hour and just a few minutes for water to penetrate about 1 centimeter through this rock. That is significantly faster than some of the other ones we've looked at today. Now back to the pumice. With its great porosity but terrible permeability, it has a low hydraulic conductivity for the amount of pore space it's got. It'll take about a half hour or so for this water to penetrate 1 centimeter into the rock. That's a lot faster than some of the other rocks, but what makes it remarkable is the fact that this rock is about 70 to 80% air. Is just amazing that it takes so long for water to get anywhere in it. In contrast, here's the scoria with its similar porosity, but great permeability and incredibly fast hydraulic conductivity. How fast does water move through it? Well, you can watch it soak right in here. Water can move through scoria up to a distance of about a football field per day. The amazing permeability and hydraulic conductivity of scoria is perhaps best illustrated at Bernie Falls, one of the most amazing waterfalls I've ever visited in Northern California. Now, I don't have video because I visited long before I had a YouTube channel. All I've got are the still photos. But do you notice anything unusual about this waterfall? Like, for example, the fact that most of the water isn't coming over top of the rocks, it's coming through the rocks themselves. Bernie Falls flows over and through the scoria rock units that underlie the river. In fact, there's more water flowing through the scoria than over it. This water is traveling through the scoria not in centimeters per year, but in miles per hour. It is really booking. In fact, the water continues to flow out of the hillside downstream in several locations for reasons we'll discuss in a few minutes, or maybe in a few days, depending on how I've edited this video. Bernie Falls is one of the most awesome waterfalls I've ever seen in my life, and I have seen almost all of them, frankly. It's a place where the water comes falling out of the rock instead of over it. It's located about halfway between Lassen National Park and Mount Shasta in Northern California, and it is well worth a visit if you're ever in that area. All right, enough of these boring waterfalls. Let's get back to the exciting stuff. Right here, I've got a glass full of unconsolidated sand. Unconsolidated sand is really the gold standard for porosity and permeability and the movement of fluids through substrate. There's a lot of empty space between the sand grains, and because those sand grains are not cemented together with minerals, there's a lot of permeability and fluids can flow through it very easily. Forget about placing a single drop of water on here. Let's just pour a whole glass of water in and watch what happens. We're talking not centimeters per year or per century, we're talking centimeters per second here. And you can see it can absorb a huge amount of water because it has so much pore space in there. While pumice and scoria may not be very common globally, unconsolidated sand, especially at shallow layers in our crust, is actually very common. And these are the best units for drilling into to get anything out, really. Now, these properties are important in a number of ways. For example, every single landfill on the planet, at least every single landfill that's been responsibly built, has a layer of clay at the bottom. This isn't a coincidence. They're not just building these landfills in places where there happens to be clay. They're putting down a layer of clay. I'm not sure exactly what the thickness of clay is in most of those cases, but I would guess it's probably around a foot of clay. Now, here's the thing. Clay can have a very high porosity. It can hold a lot of water. So why do they use clay to line these landfills? Well, because clay has a very, very low permeability and extremely low hydraulic conductivity. So even though there's a lot of pore space in between the tiny platy crystals within a clay, those tiny platy crystals tend to overlap and lock together and not allow the water to flow through. In fact, if you take the inverse of hydraulic conductivity, it tells you how long it takes for a fluid to move through the material. And it takes about 1 billion seconds for water to travel 1 centimeter through most clays. 1 billion seconds per centimeter. That's kind of insane. And keep in mind that they're putting down a layer of like 30 centimeters of clay, probably minimum in most cases, to line these landfills. So how long does it take for contaminated, nasty landfill water to penetrate through the clay and make it into the groundwater? I can't do that math in my head, but I'll do it later during editing, and there it is. So if the landfill is well built, there's no chance of contaminated groundwater making it through during any of our lifetimes. Now, of course, not all landfills are well built. I know that from experience. I've actually mapped groundwater contamination plumes from leaking landfills. So this is not to say, hey, every landfill is safe, but well-constructed ones don't allow any water through because of the low permeability and terrible hydraulic conductivity of clays. Now, porosity and permeability, hydraulic conductivity, are extremely important in building wells. Now, in oil and gas, you want to drill into a unit that's got a lot of oil and gas in it. Otherwise, you're wasting your time, right? Well, you want to drill into something with very high porosity that stores a lot of that material. But sometimes those high porosity materials don't have a lot of permeability. And so the solution used to be, okay, well, we'll just create a field of oil wells where every oil well is spaced, 20 or 30 feet from the other one, and we're just going to drill and turn this whole landscape into a really nasty polluted Swiss cheese. And then they discovered, oh, wait, there's better high permeability, high porosity units that contain oil and gas out in the Middle East and in places in Texas. We'll go to those places. And then they started to exhaust those supplies. And they realized, well, we can go back to those places where we couldn't get the oil out because there was poor permeability. And we can hydraulically fracture those rocks. We can pump water and other fluids down and shatter those rocks, create that permeability, connect those pore spaces, and then extract a lot of oil and gas from a large area with just a single well. And that's what fracking is. A lot of controversy about it. If done properly, it's very safe, or at least it's not terribly harmful for the environment. Of course, the use of all fossil fuels is bad for the environment. I'm just talking about the fracking process itself. And if done irresponsibly, it is devastating for the environment. It's nasty stuff. And we're not going to go very far into that because that's a tangent here. But that's the way in which porosity and permeability are probably most important to most geologists in the oil and gas industry. Permeability and porosity are also important in digging water wells. If you've got a well on your property, you want it to go into high porosity rock. You want it to hold a lot of water and be able to get a lot of water out. But that doesn't do you any good if your unit that you're drilling into is impermeable. Why is that? Well, if the water can't flow from the surrounding rocks into your well, then your well is going to dry up within a day or two. It's not going to work. You need to be able to draw all the surrounding groundwater into your well. Think of it like if you've got an overly cold Slurpee and you set your straw into the Slurpee You take a drink, oh, that's some good Slurpee. And you take another drink, oh, fantastic stuff. And then you take another drink, and all you're getting is air now. Now you're just sucking air through the straw, and you look in there, and your Slurpee level hasn't gone down at all, but you got this little ring of air around your straw. You've sucked all the surrounding material straight into that straw, and nothing else is making it into the straw. That's what happens when you have a well in an impermeable rock. You could have all the Slurpee in the world, all the water, all the oil and gas in the world surrounding it, but if it can't flow to the straw, your well, it's useless. Now, drawing water from a well does impact the water table and the groundwater flow around that well. And it does so in a fairly predictable way. Again, going back to our Slurpee, if you have a very slushy Slurpee, pretty well melted, not fully melted, but very slushy, you may notice that as you're drinking it, the area around the straw drops down while the stuff along the edges kind of stays up a little bit higher. And as you drink it down further and further, it's going to slope steeper and steeper down into it as it flows in towards the straw. A well does the exact same thing. All right, I've just drawn a topographic map, but a topographic map of what? Well, you can actually map the elevation of the groundwater surface of the water table beneath the surface. And so this is our elevation here. It is 5 feet deep, 6 feet deep. We're just going to say this is a level surface that we're at. We're not going to worry about the mechanics of this or whether this is the correct way to draw one of these maps. This is not a full-on geology class. If you want that, take a hydrogeology course. It's really interesting stuff. But 5 feet below the surface, 6 feet, 7 feet, 8 feet. So if you're drilling down to the water table right here, you have to drill down 5 feet. If you're drilling down to the water table here, you drill down 7 feet, and so on. It's exactly the same as a topographic map that shows the elevation of the ground surface, except now we're looking at the elevation, or rather the depth, of the groundwater surface of the water table. Now, if you place a well, let's say we'll put our well right here. We're going to drill our well right there. Well, as water gets pulled up out of the well, it's going to lower the water surface in that area. And so it's going to change the topography of our groundwater. So let's say they're using a lot of water. Maybe it's a farm, maybe it's someone who just likes to take really long showers. You might end up with a zone here where it is 10 feet below the surface, 9 feet below the surface, 8 feet, 7 feet, 6 feet. So you have this cone, and we actually use that expression, the cone of depression, where the water is being pulled down and removed from the system there. And so a well can significantly change the flow direction of the water and the depth of the water. Now, how do we understand the direction of flow of groundwater? Generally speaking, not always the case, but again, we're not getting into weird cases here. Water flows at a right angle to the topographic lines. So it wants to flow downhill, so to speak. It's gravitationally driven in almost all cases. And so your direction of flow for the water is going to be here, like so. Up here, it's going to be going like that. But what's going on here? Well, the direction of flow is going to be here. But now the direction of flow, right angles to the lines, is going to be like that. All water flowing into the well. Now this is a great example of why you should never, ever build a well near a septic tank. And this is a thing that happens a bit too often. And a bit of a gross story, and I don't know if this is actually the case. There's a contamination plume involved also from the nearby Air Force Base. But I had a family member who was complaining that, boy, lately the water coming from my well just smells like crap. It's brown colored. I don't want to drink it. You know, I don't want to bathe in it. I'm washing my clothes in the laundry machine. It's brown. It smells like a freaking outhouse. It's disgusting. And I said, well, do you have a septic tank on your property? She said, yeah. I'm like, I got bad news. It may not be a coincidence that your water smells like crap. Well, why is that? Well, because you might have a situation where your septic tank has been placed, and I'll make it green. I'll say your septic tank is right here. Let's say they put it in responsibly, and they put it in over here where the groundwater is lower, and your well has been put in right here where the groundwater is higher. Well, so the groundwater flow direction is going like this, right? So nothing to worry about, right? All the nasty stuff from your septic tank is going to flow over here, and it's not going to go against the direction of groundwater flow. It's not going to flow upstream to your well. So, hey, you're safe, right? Well, here's the problem though. As you're using tons of water and it's running down your sink and into your septic tank, you are drawing down the water here and putting in extra water right here. All right, now you've got a situation that looks like this. Water is being pumped into your septic tank, raising the groundwater level and changing the elevation of the water table around it. And water is being pulled out of your well and lowering the water table. And keep in mind, the water flows at a right angle to the contour lines. And so your water now, instead of flowing this way to the right, is here flowing this way. Here's flowing down this way, this way. Guess what? You're drinking crap. So, permeability, porosity, the direction of flow of groundwater, these things can be incredibly important if you live in a rural area and you're relying on well water and a septic system to take care of all of your water needs. Well, that was a little bit gross, but important. Now let's talk about what happens when the water table intersects the ground surface. What happens when elevation drops below the level of the water table? For that, I hope you'll join me in part 2 of this series, where we'll visit Iargo Springs. We will talk about how springs work and how they form, why they exist where they are. We will talk about the feedback mechanism and the way groundwater controls river heights and vice versa, how river heights control groundwater elevation. We'll even explore how the groundwater level will affect how deep a canyon can carve itself. I hope you'll join me for that. Until then, have fun out there.